Our first speaker is Professor Sabrina Maniscalco. She's Vice Director of our Center of Excellence and leader of Turku Quantum Technology Group.
Okay, hi everyone. As Teiko said, I'm the head of the Theoretical Physics Laboratory in the University of Turku, and I'm also an adjunct professor in Aalto University. What I would like to do today is really not to talk much about a specific research line of the Turku Quantum Technology Group, but instead I would like to discuss with you about some general reflections and ideas. And in particular, I would like to tell you 3 stories. One relates to the past, the second one is something connected to our present times, and the third one has to do with what I think is a possible vision of the future and what is our role as Turku Quantum Technology and as Quantum Technology Finland in general, a center of excellence within this future, for this future. And however, I want to begin by introducing the Turku Quantum Technology and the theoretical physics researchers. This is how we see ourselves, like this bunch of superheroes fighting the evils of the broken academic system. And you will see some of these people here, and we are not all here, but some are here, and I will, at the end of the presentation, I will just highlight some of the research questions that we are investigating, and I will ask the people who are here to stand up so that you can see them and then discuss with them later. So what is the timeline? I'm going to talk about computers and then about quantum computers, and I'm going to begin from the very, very, very beginning. That is the 1936 paper by Alan Turing, which is the principal originator of the idea of computer. And I will continue with something which is more related to quantum and quantum computer with David Deutsch, 1985. I will discuss a little bit about the current era of noisy, small-scale quantum devices, and then speculate about quantum advantage. But let's begin with the past, and we begin with Alan Turing, as I said. And I would like to say, for each of these 3 points, past, present, and future, at the end I will discuss a message, a very simple message that I would like to convey to you, and I would like you to remember. Now, the paper that Turing, that led to the whole beginning of the idea of a universal quantum computer, was a paper with this title, and this paper was not about industry, was not about gadgets, was not about future technological advances. It was about a very, very fundamental problem related to mathematics. It was related to a problem presented by Hilbert in 1928, which had to do with what are the limits of human knowability of mathematics. I don't know if one can say knowability, but what humans can know about mathematics in principle, and what, if any, parts of mathematics will be forever unknowable to human beings. So it's a very fundamental type of question. And the answer to this question was something that really led Turing to speculate about ideas that then eventually led to a whole new industry and a whole new concept. So the first step, the first thing he had to do was to discuss or think or formulate this question in terms of an algorithm. What is an algorithm? And speculating about algorithm led him to describe what is now known as the Turing machine. So this was his attempt to formulate a definition of algorithm. And this, we know nowadays, the Turing machine is a single, universal, programmable computing device that Turing argued could perform any algorithm whatsoever. So it was with this idea in mind that he actually laid the foundation of modern computing theory of computation. Now, what was perhaps left in his thinking? This was a very heuristic argument, was a very heuristic way of defining an algorithm. What happened in 1985 was that David Deutsch started to think about the fact that algorithms are always implemented in physical devices, in physical systems. So information is carried out through a physical process. And he reformulated slightly this concept in terms of what and whether there exists a universal computing device which can efficiently simulate any other physical system. Because if the answer to this question is yes, then obviously this physical device will be always able to perform any algorithm, right? And in this new formulation of David Deutsch, this is connected or closely connected to what is one of the main questions that nowadays the outbreak of quantum technology is trying to answer to. So proving or disproving quantum advantage, actually to be precise, proving or disproving whether or not a real universal quantum computer can be created really amounts nowadays at tackling a question about the fundamental limits of what is physically computable in nature. And this is a very fundamental question that has, of course, a lot of implications that are not only technological, but they are philosophical, and they have an impact that extends really to society. So my first message is, computers were born from the answer to a question which is driven by pure intellectual curiosity. And therefore, especially nowadays in the current situation, we should remember that it is very, very dangerous and risky to kill fundamental research. So we have to more and more, even I would argue more than before, we need fundamental research. And the reason why I said more than before will be clear as we go to the second part, or the second story of my talk about the present, okay? And this story is a bit different because it has to do with a book that I read when it was firstly published, Reinventing Discovery by Michael Nielsen. Probably some of you have heard about Michael Nielsen, and probably some of you have read his monograph on quantum information theory, Nielsen and Chuang. Is a very, very famous book. But Michael left academia and he started to think and speculate about several aspects, and one of his main thinking is related to this idea that actually the way in which we perform scientific research is changing, and is changing drastically. He claims that there is this collective intelligence that needs to be considered and used more and more, and he says that collective intelligence works by bringing together many people's micro expertise, their their specialized knowledge in a specific area. And how can we do this? Well, one of the ways is to use new online software and tools. What he says is that there is a mine of untapped knowledge online. How can we use it? Well, he's specifically thinking of a number of software tools that will be able to amplify collective intelligence by creating what he calls an architecture of attention for a community of practice. And this is important because will always lead to a better integration of science into our society. Now, all these words may seem quite unclear at this point to you, and you may be thinking, what are we talking about? I will give in a moment an example of what this means, but basically his main point really in his words is that there is actually currently a slow revolution that has been growing in the recent years. And this revolution is something that many scientists are not yet aware of, and they are not acknowledging. And this is really something that needs to be tackled, and we need to consider more and more. And I will give now a specific example that I've been recently more in contact with, I've been experiencing more closely. And this has to do with the way in which IBM, a big company, is doing research and tackling the problem of quantum advantage, okay? They have created this so-called Q network, which is made of a number of different actors, companies, academic institutions, startups, national research labs, and brought them all together to collaborate on tackling a very, very important problem, which is understanding or proving quantum advantage. So they have this vision, right? But the way in which they are implementing this vision is precisely following the idea of the 2011 book of Michael Nielsen, Reinventing Discovery. They are building a community. They are building a community of users which is growing larger and larger, and which is working, I would like to say, almost for them, okay, and for free, and just for the pleasure of tackling a certain challenge, okay. And specifically, referring to IBM Q Experience, that is this online quantum computer that is available to everyone. Remember, Q Experience was, there are different, actually, this is not important, different devices, but Q Experience is something which is relatively recent, okay? The framework, the software platform to operate it, Qiskit, was released in 2017, so in March 2017, so just 2 years ago. And since then, there have been more than 150,000 uses of or downloads of the Qiskit thing. 7 million experiments were performed, and over 140 research papers. Okay, these are huge numbers for 2 years. Okay, and we have been participating recently to a hackathon that brought together 135 people, organized by them, 135 people from several countries, several universities. There were high school kids, PhD students, postdocs, members of people belonging to companies, and all these people have been working together and are continuing to work to tackle important questions, research questions related to quantum advantage. So this is just, the reason why I want to talk about this is simply because I want to highlight that actually this is happening. And it is possible nowadays to just make experiments where you generate a 4 qubits entangled state with superconducting qubits, and you measure, do full tomographic reconstruction of the state with 98% fidelity. You can do it, anyone, I can do it online, it's there, okay? You don't need a lab. Now, what I want to stress is that this is a new paradigm for research, which is based on open source, online, collaborative quantum experiments on the cloud. Okay. And this is going to change the way in which we do research. It's already changing the way in which we do research. And my claim is that we need to take into account for the future. And of course, this is relevant also for our centers for quantum technology. And right here, what Jukka has been already mentioning as one of our grand challenges, to show you how strongly connected this is to what we also want to do, okay? We want to create a pilot quantum simulator, and we also write that we want to offer open remote access to this device. So my question is, how are we going to compete? Okay? And I try to give an answer to this by in the last part of the talk. And the last part of the talk is about the future and the vision I have. Okay, and the future, I believe, must rely, and this is something that we have to do, start doing here already in our Center of Excellence. What we need to think is really how to start thinking in a broad way, in a much more multidisciplinary way, encouraging much more collaborations among our groups, and focusing on fundamental research also, and also enlarging the platform of science end users and collaborators as much as possible. Because this is what is needed in the new era of scientific research. And I think we can begin right now with our March meeting, and in particular, what we can do already now is talk, interact, learn, go to sauna, and discuss. Because we are already having within our Center of Excellence a huge variety of expertise. So we need to do it because this is what is required, I believe, nowadays by our by the new revolution that is going on. But also, thinking in a larger framework, we are both at Turku and at Aalto involved in a project. It's a multidisciplinary research and art project which brings together physicists, computer scientists, game makers, artists, all together to explore quantum technologies through games and playful art. And I would encourage all of you, some of you are already participating, but I would encourage all of you to learn more and participate to this type of projects. And finally, I would like to now conclude my talk by telling you just a few of the questions. They are just the questions, I will be very brief, that we tackle in our Turku Quantum Technology Group. And the reason why I'm doing this is that I would like you to go and talk to the people who are here about this question so that we can more and more increase our collaborations within the Center of Excellence, explore more fundamental research questions and establish new interdisciplinary collaborations. And the first scenario is a scenario which has to do with open quantum systems. So we study how we can engineer environments, possibly using also quantum optimal control for engineering environments in order to somehow make better quantum devices and quantum technologies, to improve quantum devices and quantum technologies. We focus also on quantum simulators of specifically Markovian and non-Markovian systems, and we also studied some relativistic effects and some fundamental questions like quantum Darwinism. And the people who are here and working on open quantum systems research at the moment are Jose, can you do like this, stand up so that people see you. Jose there. Matteo is also working on open quantum system. Gia, you are starting to work on open quantum system there. And I think I'm not missing anyone for now. This is the main people at the moment. There are others, but they are at home, unfortunately sick. Some of them. Second question is about complex quantum networks. There is a poster tomorrow. The people working on complex quantum networks, and in particular on the interplay between quantum advantage and topology of the networks, and several questions related to these, are Gia, again there, and Matteo, who is here. Then we have another topic, and another posters of tomorrow has to do with transport and modeling transport in many body quantum systems. And here there is Walter, and where is him? There you are, Nicola. Show yourself. And then now I'm flashing three very basic fundamental questions that are related to quantum metrology, quantum communication, and quantum measurement problem. Does one have to learn everything to learn something? Do we really have to use quantum tomography all the time to learn something about the states? Teiko here and Oskari. Okay, there. Teiko and Oskari also are the people who are behind the second question. What kind of communication tasks a quantum system is, in what type of communication task a quantum system is better than a classical system? And finally, last question is how to gain information with minimal disturbance. So they are topics, fundamental topics related, as I said, to quantum measurement, quantum communication, and basic research in quantum information theory. Now, I will conclude with the three main messages that I already gave, and I just want to recall them here. The first one is the quantum technologies race, the flagship, and all these is not just about technology industry. Okay. There is a lot of very important fundamental questions that are behind and will be answered as we proceed in this direction. Second question is the way of doing research is changing dramatically, and I think we need to acknowledge and embrace this change and be more open to collaborative and different type of research, which may include different media. And finally, we need to dare to get out of our comfort zone in order to do this, because this is really pushing us in directions where, you know, we are not super expert about. So it is always a little bit uncomfortable. And I also believe that we need more fundamental research now more than ever. And this is all. Thanks for listening.
Thanks a lot. These were many things to think about.
Yeah, nice that you took this remote use of this IBM as an example. I think that now our QTF and the predecessors of the QTF, the idea has been that we want to do some things that are a little bit off mainstream, which means that we are developing detectors, we are developing instruments that do not exist. So I hope this part remains. But I agree fully that there are areas like what you just presented where it's better to change the research plan and really go for not making things or everything ourselves, but using what is already available around.
But let me clarify. What I wanted to do is to put forward a provocation. I think that what we are doing in the Center of Excellence is different. But I think, precisely, but I think that we need to also both exploit and collaborate when it comes to things which already exist. And so I'm just repeating what you are saying. And at the same time, what we need to do is to think creatively and in a much more fundamental way about what are the possibilities, exploiting our expertise, but also exploiting what is available and clarify what are the differences and the future directions. Yes. No, but I precisely agree with you. So it was the reason why I wanted to point it out.
I think it's great that already the first talk gave so many thoughts that we could just stop here and have discussing about these things full day, but we have to continue. Let's thank Sabrina again.